Hi everyone, welcome to video number 2000 made for this channel. On this occasion I propose a look back at some of the highlights of the last 1000 videos. So let us start with video number 1100, which is on the Allen-Kahn equation on the sphere. I had already done videos of this equation on the plane or on the torus. So the Allen-Kahn equation is a reaction-diffusion equation that describes phase separation. For instance, if you have a mixture of oil and water or different phases in an alloy which separate over time. So what's new here is that I've simulated it for the first time on a sphere. I had done this before for the wave equation, but not for a reaction-diffusion equation. And the difficulty when you do this is to choose the simulation mesh. The most obvious choice is just to discretize longitudes and latitudes, but then the problem is that you get a lot of points near the poles, and the Laplace operator in spherical coordinates will diverge at these poles. The two effects should compensate, but when you do numerical simulations, round-off errors produce some strange artifacts, as you will see if you look closely at this video. I managed later to improve this by changing the simulation mesh. So what I did was to use a mesh on a cube projected on the sphere and optimized. But for now, this is done with a longitude-latitude mesh with a little bit of regularization at the poles. So this video was published in February 2024, and it took a bit over 41 minutes to render. The color scheme is called Twilight, and the soundtrack is Ether by bobbyrenz at MacDougall. So let's have a look. I had made simulations of the Euler equations for hydrodynamics on the sphere before this one, but what is new here is that I added the continents of the Earth. As a result, we get a simplified approximation of a weather simulation, though it has a certain number of deficiencies. In particular, I think the Coriolis force is not chosen of the right order of magnitude, so the pressure systems you get are not as stable as one would like. So this simulation was published in May 2024. It has 4 parts, showing first the density, which is related to pressure, and then the wind speed in 2D and in 3D. And it took a bit over 1 hour, 1.5 hours for each part to simulate. The color gradient is Viridis for the density part and Parula for the wind speed part, and the soundtrack is Pixelated Autumn Leaves by Jeremy Blake. Video number 1300 is the adaptation of another equation to spherical geometry with the Earth's continent. In this case, it is the shallow water equation, which models a fluid which is much wider than it is deep by a 2D equation that's easier to simulate. There's a parameter in this equation which measures the amplitude of typical wave divided by the depth of the fluid, and this simulation takes two different values for this parameter, but which would correspond to oceans which are much shallower than they actually are on the Earth. Also, the radial scale is exaggerated a lot, so that it's easier to see what happens. And it's also shown in 2 and 3 dimensions. So this simulation was published in September 2024. The different parts took between 1 hour and 1.5 hours to simulate. The color gradient is Viridis, and the soundtrack is Erik Satie's Gymnopédie numéro 1. Video number 1400 I had a lot of fun making. For a while I had been making simulations of interacting polygons, which is surprisingly difficult to get right because my simulations are basically based on Newton's equations, which do not allow directly to have hardcore interactions. So you have to replace those by potentials which are stiff but smooth interactions. And in addition, I had started adding devices like conveyor belts and sieves to the simulation. So in this one, I wanted to put as many elements as I could in one setup, and the video follows the journey of one particular particle in this setup during several revolutions. It was published in December 2024, and the render time was 1 hour 21 minutes. The color gradient is Strobo, and the soundtrack is Smooth Sailing by Audionautics. Video number 1500 is actually inspired by some of my own research. It concerns a version of the Kuramoto model of coupled phase oscillators. Kuramoto models describe entities called oscillators, which are described by an angular variable called a phase, and depending on the interaction you put, they can synchronize or not. So one option that is often used is an all-to-all coupling called a mean field model. Now in the version we look at here, it is different, so each oscillator is only coupled to its 4 neighbors. And in the work we did, that was for a one-dimensional version, and there we were able to find all stationary states of the system, which are characterized by something called a winding number. And when you add noise to the system, you can actually jump between states with different winding numbers. In dimension 2, the system is actually equivalent to what is known as the XY model in statistical physics, where the different angles describe orientations of spins, which can turn in the plane but always have the same length. Now in 2D the situation is more complicated, so this winding number is something will be replaced by something like the total vorticity, and you have more freedom in how the system can go from one state to the other. So this you will see it has the effect of having vortices in the system around which the phase turns by a full turn, but vortices and anti-vortices can merge and disappear. So this simulation was published in March 2025, and it took 1 hour 20 minutes to render. The color gradient is Turbo. The soundtrack is Future Freeway by MacDougall. And it shows 2 simulations with slightly different parameter values and with and without noise. The next simulation was my first simulation of the Keller-Segel model, which is a model for chemotaxis, meaning that you have a certain organism which will move according to the presence or not of a nutrient. So it's a bit similar to reaction diffusion equations, except that the interaction is a bit more complicated. So what you have is you have two populations. So one is the nutrient, the other is your organism feeding on the nutrient. So the nutrient reproduces itself, and the organism has a tendency to move against the gradient of the nutrient, meaning that it will actually go to regions where the concentration is higher. And this leads to interesting spatial structures. So this simulation was published in June 2025. It contains simulations with two different parameter values, and the two different simulations took about half an hour to make. The color gradient is Viridis and the soundtrack is Dream Escape by The Tides. Video number 1700 is my first simulation of interacting particles on a sphere. I've done many more simulations in that geometry since this one. So, to have interacting particle on a sphere, what you have to do is that you have to measure correctly the distance between particles. That allows you to compute the interaction, which is in this case a Lennard-Jones interaction, and then also to render this correctly in 3 dimensions. So this is, as I said, my first simulation on that kind of system, so it simply consists in a bunch of particles on a sphere with different velocities, and they interact, and their color represents their kinetic energy. So it was published in October 2025. The render time was 18 minutes for the 3D version and 1.5 minutes for the 2D version. That's because my way of rendering 3D is maybe not optimal, so it takes some time to compute. The color gradient is Turbo, and the soundtrack is Sunday Skate and Golden Gate by OtisMacDonald. Video number 1800 introduces another reaction diffusion equation known as the Gray-Scott model. This is a model for chemical reaction where two A molecules encountering one B molecule transform into three A molecules, and it leads to really beautiful patterns such as mazes in this case, but you can also have gliders, you can have space-time chaos, and so on and so forth. So this simulation here was published in January this year, 2026. It took 47 minutes to render in 2D and a bit over 1 hour in 3D. The color gradient is called CVDs and the soundtrack is Kayak by the Grey Room Density and Time. Video number 1900 is my first video of the wave equation with Neumann boundary conditions. Up to that point, all my videos of the wave equation in some domain use Dirichlet boundary conditions, which means that the value of the wave is 0 outside the domain and actually has to go to 0 when you approach the boundary. So this is good for systems like a drum, because the membrane of the drum is fixed on the boundary. It's also good for sound waves in a domain because the amplitude of the oscillation is 0 at the boundary. But it is not so realistic for instance, water waves, because what happens instead is that actually the water height can change at the boundary, but it tends to be horizontal there. So this is called Neumann boundary conditions, and to simulate them is a bit more tricky. So the way it is done is that you add some ghost points which are in the boundary outside the domain but next to points in the domain, and you change the update rule for these particular points in such a way that this condition on the derivative is satisfied. So this simulation I published on April, 25th April this year, 2026. The render time is 30 minutes for the 3D version and 16 minutes for the 2D version. The color gradient is Viridis and the soundtrack is Saucers Unaware by Jade V. Alright, so this concludes our little look back at the last 1000 simulations on this channel. So you may ask what's next, and I'm actually getting a lot of good ideas and comments, and I might try implementing some of them in the future. So one comment I get quite a lot is, could I do interacting particles in 3 dimensions? That is possible to do. One difficulty is that all my code will have to be adapted to 3 dimensions, so all positions, velocities, forces, and so on have to be computed in 3D. I know how to do it, but it will take some time to adapt the code. And another difficulty is how to render this in 3D. Now, another point is, for a while I made a number of tutorials that either explained how I make the simulations or addressed some problem in science. And this I would really like to do more of these, but in the last couple of years I've been very busy with my main job, and I didn't really find the time to do it, but hopefully at some point I will do some of these tutorial videos again. And another suggestion I am getting quite often is, why not try other non-Euclidean geometries than the sphere? So my simulations are either on the plane or on the flat torus, meaning you take a plane or a rectangle in the plane and you identify opposite boundaries, or the sphere. We've seen many of those in this retrospective. Now, one could imagine, for instance, a real torus, like the surface of a donut, or hyperbolic geometry, so the geometry of a saddle. This can all be done, but again, it takes some work because one has to adapt computation of the distances, of the Laplacian and so on to these geometries, and also adapt visualization. So perhaps I will do some of these things in the future, so we shall see. And maybe there will be another retrospective after I reach 3,000 videos. Who knows? So thanks a lot for doing this retrospective with me, and we will continue tomorrow with regular simulations. So take care.